When we said that we had conservation of energy, we basically were saying the initial energy is equal to the final energy, where the energy is a combination of kinetic and potential. But the restriction that we put on it when we said that energy was conserved is that we could only have conservative forces acting on the system. And so we could get caught up in a circular argument in terms of trying to define what a conservative force is. We could say, well, a conservative force is a force where when it acts on a system, the energy is conserved. And then we'd say energy is conserved when only the forces that are acting are conservative forces. That's a circular argument because it never really accurately defines for us what we mean by a conservative force. So here's the definition from your book. It looks kind of complicated, but let's kind of condense it down and say what it says. You know, here they're talking about the work done by a force and going along a path. The path goes from point A to point B. And what they're trying to show here in the first line, that's numbered 8.8, is that for a conservative force, the work done taking path 1 would be exactly the same as the work done in taking path 2. In a more broad sense, the definition of a conservative force says that the work done by the force is independent of the path. That's what this kind of means right here. It just means that no matter how you get from point A to point B, you will do the same amount of work. And that's what this is saying. So one way to define a conservative force is that the work that that conservative force does in going from point 1 to point 2 doesn't depend on the path. Sort of another way to state that is that if you have a closed path, which means you begin and end at the same point, then in that case the work done as you go in that closed path would be equal to 0. I like the path-independent idea of work because I feel like it's a little easier to see. And we're going to use two examples. We're going to use gravity and the work of a spring. So if I have gravity acting on an object, and let's say I have, here's my object, here it's at point Y initial, and up here it's at point Y final. Here's the force of gravity. And what if I wanted to find the work done as I went from the initial point to the final point? Well, the work done is equal to the force dotted with the displacement. And it just turns out, I think using the unit vectors makes it easier to do it because gravity's acting down, but we're moving the box up. So the force is in the negative y direction. Our displacement is y final minus y initial. It's also in the y direction. And so our work done is going to be minus mg times y final minus y initial. Now, what I would like to think about is how would this change if I didn't go, like, right now I think I'm kind of assuming I start here and I go here, that this is my path. But what if I went here and then here and then here? What if that was my path? Would my work change? And the answer is no, because as I would go horizontally, gravity wouldn't do any work. It would only do work in this point, which is exactly the same as this portion. And likewise, there's no work done here because the force and the displacement are perpendicular to each other. Similarly, this would be more complicated to do the math, but if this was another path and I was trying to calculate the work done there, I would really only find, here my displacement would have an x and a y component, but the x component of the displacement at any portion of this path would not contribute to the work because the force is strictly in the y direction. So once again, the work would only be dependent on the displacement. And so hopefully we're starting to see what we mean by independent of the path. And we can also see it in this expression here. The work done by the gravity really only matters where I start, y initial, and where I end. It only really depends on the endpoints. It doesn't depend on what I'm doing in between. The work doesn't change depending on how I got from the initial point to the final point. We just showed with 3 different paths would all have the same work. This is a characteristic of a conservative force. It really only matters where I begin and where I end. It doesn't matter how I got there. Finally, if we think of a spring, and just let it move back and forth. Maybe this is my x equals 0. And I could maybe go between the mass on the spring is here at the initial point, and maybe it's here at its final point. I didn't add the spring because I thought it would make the drawing too messy, so I hope that's not confusing. I'm assuming that the mass is still attached to the spring at both of these locations. But we did see that for the work done by a spring, and we did this calculation a while ago, that the work done by a spring depended on its initial location and its final location. And so what I didn't want to really, it's hard to draw this because it's all along, the motion's along the same line. The work done by this spring doesn't matter if I started here and went right to this final point, or perhaps I started at this initial point and it oscillated a couple times and then I looked here, or any other sort of combination of motion that would happen between the initial and the final point. As we see in this expression for the work done by the spring, it only depends on where I start and where I begin. Again, this is a path-independent value for work, and that makes the force of a spring a conservative force. Now, if you wonder why I've chosen gravity and spring as my examples, it turns out that for a while, these are going to be the only conservative forces that we know about. And if you want to connect more dots, you might keep in mind that these are the potential energy functions that I've also learned. It turns out that only conservative forces have potential energy functions associated with them. So we've just explained how gravity and the force of a spring are conservative, but you also realize that these are 2 examples of potential energy functions as well. It's not a coincidence. It's actually, they're directly linked. We have potential energy functions for these 2 forces because of the fact that they're conservative forces. And so when I have a scenario where springs and gravity are the only things that are acting, I can include them by virtue of their potential energy functions, and then I also would have a scenario where energy is conserved.